तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed concrete structures. This is the second lecture of module 4 on design of members. In this lecture, we shall learn about the design of sections for flexure. We shall learn the steps of final design. Specifically, we shall learn the final design for type 1 members, and also we shall see a special case of type 1 members. For design under service loads, the following quantities are known: MDL, the moment due to dead load, which excludes the self weight, and MLL, which is the moment due to live load. These two quantities are available from the analysis of the structure or the beam. Next, the quantities that are unknown to us are, first, the type of the section and the properties of the section. Second, the moment due to self weight, and we also do not know the area of the prestressing steel, which is denoted as AP, then the effective prestress PE, and the eccentricity E. The material properties are selected before the design. Now, as we had mentioned last time, that the design procedure is divided into two stages for convenience. The first stage is called preliminary design, where we do the estimates of some quantities and then we do the final design. In the preliminary design, we first select the material properties, the FCK, which is the characteristic strength of concrete, FPK, which is the characteristic tensile strength of the prestressing steel. Usually, these materials are selected based on the material that has to be supplied by the supplier. Next, we determine the depth of the member. This is also usually governed by the architectural requirement. Now, if there is no architectural specification, then we can determine the depth by some empirical equations, which is based on the moment that we have from the dead load and live load. Next, we calculate the section properties. Before that, we select the type of section. Now, the sections can be either a rectangular section, T section, or inverted T section. Now, the type of section that is used depends on the type of application, and we shall discuss about this in a future lecture. Once we have selected the type of section, we can estimate its self weight, and then we calculate the total moment, which includes the moment due to dead load, live load, and the moment due to self weight. After this, we estimate the lever arm. The lever arm is expressed as a fraction of the total depth. Then we estimate the effective prestress. The effective prestress is equal to the moment divided by the lever arm, and from the effective prestress we calculate the area of the prestressing steel, which is given by the prestress divided by say 70% of the characteristic strength, and finally we check the cross section A to make sure that it is not too way off from the allowable stress which is expected near the CGC. Thus, the steps of preliminary design is to have estimates of the area of the prestressing force, the prestressing steel, and the type of section, but we do not know one important variable yet, that is the eccentricity of the CGS. Next, we are moving on to the final design, where the objective is to calculate the eccentricity and to check the compressive stresses in the concrete. Now, before we move on to the steps, let us know the type of sections that the code allows us to design for. The code IS 1343-1980 defines three types of prestressed members. Type 1, in this type of members, no tensile stress is allowed in concrete at transfer or under service loads. That means in type 1, the full section is under compression throughout the service loads. Second, type 2, in this type of sections, tensile stress is limited within the cracking stress of concrete. That is, we do allow some tensile stress in the concrete, but we make sure that it is within the cracking stress, and hence this section remains uncracked under service loads. And the third type is type 3, where we allow cracking, but here the tensile stress is such that the crack width is within the allowable limit. That means, although we allow cracking, we limit the crack width to a certain value so that it does not disrupt the serviceability conditions of the prestressed member. Now, the final design involves the checking of the stresses in the concrete at transfer and service loads with respect to the allowable stresses. This is a very important step of the final design, that we need to check the stresses in the concrete. Since the allowable stresses depend on the type of member, type 1, type 2 or type 3, the equations vary for the different types. Now, when we will learn the equations, we shall use the properties of the gross section instead of the net or transformed sections for simplification of calculations. We had seen earlier in the analysis of members that if we use the more rigorous calculations based on the net or the transformed sections, we do not gain much accuracy than the calculations based on the cross section. Hence, for simplicity, we are using the properties of cross section. But in a special situation, if we feel that the properties of the cross section may not lead to accurate solutions, then we may use the net or the transform section properties. In the final design, the steps are explained for type 1 and type 2 members. The steps for type 3 members are similar to type 2 members, the only difference being the value of the allowable tensile stress in concrete. That means, in this lecture, we shall first learn the design of type 1 members. In the following lecture, we shall learn the design of type 2 members. Now, we shall not study the design of type 3 members specifically, because it is similar to the design of type 2 members, the only difference being the allowable tensile stress in the concrete section. Next, we are moving on to the final design of type 1 members. Just to recollect, for type 1 members, no tensile stress is allowed at transfer or under service loads. For small moment due to self weight, say MSW is less than 30% of the total moment, the steps are as follows. First, calculate eccentricity E to locate the centroid of the prestressing steel, which is denoted as CGC. We had learned earlier that with increasing load, the compressive force C moves upward from the location of the tension T at CGS. At transfer, under the self-weight, C should lie within the current zone to avoid tensile stress at the top. The current points and current zones were explained in the module of analysis under Flexure. Thus, the lowest permissible location of C due to self-weight is at the bottom current point, which is at a depth Kb below the CGC to avoid tensile stress at the top. The design procedure based on the extreme location of C gives an economical section. Let us understand this calculation by the help of a diagram. At the time of prestressing, the C coincides with T. When the transfer is over and the member has deflected upwards, then the self-weight has started to act. Now, when the self-weight acts, the C shifts upward from T. Now, for a type 1 member, this upward shift should be such that C enters the current zone to avoid any tensile stress at the top. Thus, the lowest position of C, which is permissible, is at the bottom current point, which is at a depth Kb from CGC. Now, the procedure based on the lowest CGS and hence the lowest location of C at transfer gives an economical section. Now, when C is at the bottom current point, then the stress in the concrete is triangular with 0 at the top and Fb at the bottom. From the previous sketch, the shift of C due to self-weight gives an expression of E. E is equal to MSW divided by P0 plus Kb. Let me repeat this based on the diagram, that the distance of the CGS from the CGC, which is denoted as E, is equal to the shift in the location of C, which is equal to MSW divided by P0 and plus Kb, which is the distance of the bottom current point from CGC. Thus, we have got an expression of E from the quantities which are known to us. We have already calculated MSW for the section, selected section. P0 we now need to estimate from the previous values of AP, and Kb is also known for the trial section. Here, the magnitude of C or T is equal to P0, the prestress at transfer after initial stresses. That means the compression or tension is equal to the prestressing force, which is at transfer after the initial losses. The value of P0 can be estimated as follows. For a pretension member, we know that there is a loss due to elastic shortening from the value of the force that we measure in the jacks. To estimate the prestressing force after the losses due to elastic shortening, we can consider that P0 is equal to 90% of the initial prestressing force which has been applied by the jacks. Thus, for pretension members, P0 is equal to 0.9 times Pi, where Pi is the prestressing force which was measured as the jacks. For a post-tension member, we can neglect any loss due to elastic shortening if there is a simultaneous stretching of all the tendons. Even if the tendons are stretched sequentially, the elastic shortening can be neglected at this point, and hence we can equate the P value of P0 to Pi, which is the force measured by the gauges of the jacks during the prestressing operation. The value of Pi can be estimated from the amount of prestressing steel determined in the preliminary design. Pi is equal to the area of the prestressing steel times 0.8 times of FPK. Here the permissible prestress in the steel is 0.8 FPK, where FPK is the characteristic tensile strength. We had known earlier that the code does not allow to stretch the tendons beyond 80% of their characteristic strength, because there will be more relaxation loss and also because of the safety reasons. Hence, the maximum prestress that can be applied is the area of the prestressing steel times 80% of the characteristic strength. Now, once we have known Pi, we can calculate P0 depending on whether the section is pre-tensioned or post-tensioned. Once we know P0, we are able to estimate E. Our next step is to recompute the effective prestress PE and the area of prestressing steel AP. With increasing load, C further moves up. Under the service loads, C should lie within the current zone to avoid tensile stress at the bottom. The highest permissible location of C due to the total load is at the top current point, which is at a height kT above CGC, to avoid tensile stress at the bottom. Let us understand this by the help of the sketch. When the total moment is applied during service conditions, C has shifted further upwards. Now, for a type 1 member, C has to lie within the current zone to avoid any tensile stress. The maximum location allowed for C is the top current point, which is at a distance kT from the CGC. And in that situation, the stress block that we get in concrete is triangular with zero stress at the bottom. Thus, we see that for transfer and for service, we have satisfied the allowable tensile stress in the concrete, which is 0 for a type 1 member. From this previous figure, the shift of C due to the total moment gives an expression of PE. At this stage, we are recomputing PE based on the maximum shift that we can have of the compressive force. This also gives an economical section, because if we have the maximum shift, then we have the lowest value of the prestressing force. PE is equal to the total moment divided by E plus KT. Let us just understand from this figure that the lever arm is now the shift of the C, which is equal to E plus KT. Hence, PE is equal to MT divided by E plus KT. Considering FPE to be equal to 70% of the characteristic strength of the prestressing steel, the area of prestressing steel is recomputed as AP is equal to PE divided by FPE. Thus, once we have recomputed the effective prestress, we can recompute the amount of prestressing steel by estimating the effective prestressing force to be equal to 70% of the characteristic tensile strength. Once we have got the final value of PE, we are again recomputing eccentricity E. First, the value of P0 is updated. The eccentricity is recomputed with the updated value of P0. If the variation of E from the previous value is large, another cycle of computation of the prestressing variables can be undertaken. That means gradually we are converging to a set of results which gives the maximum possible E, the lowest possible PE, satisfying the allowable tensile stress in the concrete, which is 0 for type 1 members. Once we have converged to a set of prestressing variables, that means PE, AP and the eccentricity E, next we are moving on to checking the compressive stresses in the concrete. The fourth step is check the compressive stress in concrete. The maximum compressive stress in concrete should be limited to the allowable values. At transfer, the stress at the bottom should be limited to FCC allowable, where FCC allowable is the allowable compressive stress at transfer, and this is available from figure 8 of IS 1343/1980. At surface, the stress at the top should be limited to FCC allowable, where FCC allowable is the allowable compressive stress in concrete under service loads, which is available from figure 7 of IS 1343/1980. We had seen earlier that the allowable compressive stress for concrete is different at transfer and at service. Usually, the allowable compressive stress at transfer is higher because it is of a temporary nature, whereas the allowable compressive stress in service is relatively lower. Now, our aim is to check the maximum compressive stress in the concrete to be within the allowable value. At transfer, the stress at the bottom can be calculated from the average stress minus P0 by A. See here, we are doing the calculation in a simplified way. Instead of writing the stress in terms of individual components of a uniform stress and a varying stress, we are writing directly from the proportionality of the triangle, from the using the similarity of the triangle concept, since the stress block is triangular. Here we are getting the advantage of a triangular stress block. The stress at the bottom, FB, is equal to minus P0 by A, which is the value at the CGC times H divided by CT. Thus, from the similarity of the triangles, we are proportionately increasing the stress from the value at CGC to the extreme fiber. And like this, by knowing P0, the area, the total height H and CT, we are able to calculate the stress at the bottom. We have to satisfy that the numerical value of FB should be less than or equal to FCC allowable. To satisfy this, the area of the section should be greater than P0 times H divided by FCC allowable times CT. Thus, here we have a constraint that the area of the selected section has to be greater than a certain value. If the area that we have selected for the trial section is not satisfying this, then we have to redesign the section. Thus, we come to a point where the section that we have selected in the preliminary design may not be adequate, and we may have to increase the section if the area is not satisfying the minimum requirement. Next, to check the stress at service conditions, we are calculating the maximum compressive stress at the top, and from this figure we are finding out that the maximum stress at the top is proportional to the stress at the CGC, and from the similarity of the triangles we find Ft is equal to minus Pe by A times H divided by Cb. Note that here we are considering the effective prestress at service conditions. We have to satisfy that the numerical value of the stress at the top should be less than the allowable compressive stress for the service conditions, and this brings in another condition for the area of the section. A should be greater than Pe times H divided by FCC allowable times Cb. Again, just like last time, if the area of the section is not adequate for the trial section that we have selected from preliminary design, then we need to update the section by increasing its area. Thus, we have come to a stage where first we had satisfied the allowable tensile stress, we had determined the prestressing variables, then we checked the compressive stresses. If the compressive stresses are not within the allowable value, then we have to redesign the section, and we need to do this calculation once again to make sure that all the stress conditions are satisfied both at transfer and at service. There is a special case for the type 1 members. What the calculations that we have shown, those are for a member where the self weight is smaller compared to the total moment. For large moment due to self weight, that means if the self weight itself is greater than 30% of the total moment, then the eccentricity E, which has been calculated from the expression mw by P0 plus Kb, this may violate the cover requirements or may even lie outside the beam. In such cases, locate E as per the cover requirements. The analytical expression of the eccentricity that we had seen earlier will be valid if we satisfy the cover requirements simultaneously. If we are violating the cover requirements, which may occur if the self-weight moment is high, then we cannot have that maximum value of E from the analytical expression. We have to determine E based on the cover requirements. Hence, this is another constraint of the E, that the CGS should be in such a distance that we satisfy the cover requirements for the bottommost tendon. Now, when the E is determined based on the cover requirements, then the location of C at transfer will be within the current zone. Since we have not been able to push E as much as based on the analytical expression, C will also not be at the bottom current point, but it will be within the current zone without zero stress at the top. The expression of stress at the bottom is different from that given earlier. The other steps are same as before. That means for this special case, the only difference is the expression of the stress at the bottom, and this occurs when E is determined based on the cover requirements. At transfer, the stress at the bottom is calculated from this stress diagram, where the eccentricity of the centroid from the CGC is given by the eccentricity of the CGS, which is E, minus the shift due to the self-weight moment, which is equal to MSW divided by P0. Once we know the eccentricity of C, now since we do not have a triangular stress block anymore, we cannot use the proportionality equations as we had used before, we are calculating the stress at the bottom based on the individual components, that the stress equal to minus P0 by A, which is the uniform stress component, and then minus P0 times the eccentricity of C, which is E minus MSW divided by P0, times the depth of the bottom point from the CGC, which is CB, and then divided by I. Thus, here instead of calculating the stress from the similarity of the triangles, we are calculating the stress from the basic concept of the stresses, that it consists of a uniform stress block and a varying stress block due to the eccentricity of C. Substituting I is equal to AR square, where R is the radius of gyration, and R square by CB is equal to KT, which is the distance of the top current point from the CGC, we get FB is equal to minus P0 by A times within bracket 1 plus E minus MSW divided by P0 divided by KT, and this is the expression of the stress in the bottom when E is determined based on the covered requirements. We have to satisfy that FB is less than the allowable compressive stress, and once we write that inequality equation, we have the condition for A, that A should be greater than P0 divided by FCC allowable times within bracket 1 plus E minus MSW divided by P0 the whole divided by KT, and the area of the section has to be greater than this value to have the bottom stress within the allowable compressive value. The rest other steps for this special case is same as the steps for the type 1 member. Next, let us understand this design process by the help of an example. Design a simply supported type 1 prestressed beam with MT is equal to 435 kilonewton meters, which includes an estimated MSW is equal to 55 kilonewton meters. The height of the beam is restricted to 920 millimeters. The prestress at transfer FP0 is equal to 1035 Newton per millimeter square, and the prestress at service FPE is equal to 860 Newton per millimeter square. Based on the grade of concrete, the allowable compressive stresses are 12.5 Newton per millimeter square at transfer and 11.0 Newton per millimeter square at service. The properties of the prestressing strands are given below. The type of prestressing tendon that we are using is a 7-wire strand. The nominal diameter is 12.8 millimeters and the nominal area is 99.3 millimeters square. Thus, we are given the total moment, which includes an estimate of the self-weight moment. We are also given the prestressing at transfer and at service. We know the allowable compressive stress in the concrete at transfer and service. Since this is a type 1 member, the allowable tensile stress is 0. We also know the type of prestressing tendon that we are going to use. The properties of the prestressing tendons will be available from the supplier of the prestressing steel. First, we are doing the preliminary design. For this particular problem, the value of H is given, which is 920 millimeters, and MSW is also given. We are estimating the lever arm Z, which is based on the ratio of MSW by MT. The ratio of MSW by MT is equal to 55 divided by 435, which is equal to 12.5%. Since MSW is less than 30% of MT, we are estimating Z to be 50% of the total height, which is equal to 0.5 times 920 is equal to 460 millimeters. Next, we are estimating the effective prestress. Since the self-weight moment is small, the prestress will be more governed by the imposed load moment. We are calculating the moment due to imposed load MIL equal to the total moment minus the moment due to the self-weight, which is equal to 435 minus 55 is equal to 380 kilonewton meters. The effective prestress is equal to the moment due to the imposed load divided by the estimated lever arm, which is equal to 380 times 10 to the power 3 divided by 460, and this gives 826 kilonewtons. From the estimate of the prestressing force, we are estimating the area of the prestressing steel, which is PE divided by FPE. For this problem, the FPE is given, and AP is equal to 826 times 10 to the power 3 divided by 860 is equal to 960 millimeter square. We are also estimating the area of the cross section to have average stress in concrete equal to 0.5 times of the allowable compressive stress at service. A is equal to PE divided by 0.5 times FCC allowable equal to 826 times 10 to the power 3 divided by 0.5 times 11, which is equal to 150 times 10 to the power 3 millimeter square. Thus, after the preliminary design, we are having the required area of a section, which is equal to 150 times 10 to the power 3 millimeter square. At this stage, we have to select a trial section which satisfies this requirement. We are selecting an I section for this application, where the breadth of the web and the depth of the flanges are selected to be 100 millimeters. The total depth is restricted to 920, and given the area, we can calculate what should be the flange width for this particular section. The flange width comes out to be 390 millimeters. This is a section which is symmetric about the horizontal axis. Next, we are calculating the geometric properties of the section. Since the section is symmetric about the horizontal axis, the CGC lies at mid depth. The section is divided into 3 rectangles for the computation of the geometric properties. There are 2 rectangles for the flanges and another rectangle for the web in between the flanges. The distance of the centroid of the top rectangle from the CGC is 410 millimeters. To check the area of the section whether it is correct or not, the total area is equal to 2 times the area of the rectangle 1 plus the area of rectangle 2, and we are substituting the values of the rectangles, and we find that indeed the area is equal to 150 times 10 to the power 3 millimeter square, which was the minimum requirement based on our preliminary design. Next, we are calculating the moment of inertia of the section about the axis through CGC. I is equal to 2 times the moment of inertia of the rectangle 1 plus the moment of inertia of the rectangle 2. Now, the moment of inertia of the rectangle 1 is available from the parallel axis theorem, which means that we are first calculating the moment of inertia about its centroidal axis, and then we are adding a term which is equal to area times the distance square, where the distance is between the centroid of that rectangle and the CGC of the section. For the second rectangle, the moment of inertia is given by this expression about its centroidal axis, because for the second rectangle the centroidal axis coincides with CGC. Substituting the geometric values, we find I is equal to 1.6287 times 10 to the power 10 millimeter to the power 4. We are calculating the square of the radius of gyration, r square is equal to I by a, and once we substitute the values of I and a, we get the value of r square equal to 108,580 millimeter square. We are also calculating the kern levels of the section. Since the section is symmetric about the horizontal axis, the two kern levels are same. Kt is equal to Kb is equal to r square divided by Ct, and once we substitute the values of r square and Ct, we find Kt is equal to Kb equal to 236 millimeters. Thus, after the preliminary design and the selection of a trial section, we have found the geometric properties of the section, and also we have found the estimates of the prestressing variables. For the section, A is equal to 150,000 millimeter square, I is equal to 1.6287 times 10 to the power 10 millimeter to the power 4, Ct equal to Cb equal to 460 millimeters, which is the distances of the extreme fibers from CGC, and the kern levels are at distance Kt equal to Kb equal to 236 millimeters. For the properties of prestressing steel, the estimated area of prestressing steel is equal to 960 millimeter square, and the effective prestress equal to 826 kilonewtons. Now we are moving on to the final design, where we shall compute the eccentricity of the prestressing steel, and then we are recomputing the effective prestress and the other prestressing variables till we have a convergence, and then we shall move on to check the compressive stresses in the concrete. We are calculating the eccentricity E from the value of P0, P0 equal to AP times FP0, which is equal to 960 times FP0 is given as 1035, which brings P0 is equal to 993.6 kilonewtons. With that value of P0, we are computing the value of E, which is equal to MSW by P0, the shift of C from the CGS, plus the depth of the bottom kern point, which is Kb, and once we substitute the values, we get the eccentricity to be 290 millimeters. That means that is the maximum eccentricity that we can allow to have a type 1 member with no tensile stress at the top during transfer. We are recomputing the effective prestress and associated variables with this new value of E. PE is equal to the total moment divided by the shift in the compressive force, which is the lever arm, and we know E equal to 290, Kt is equal to 236, and the total moment is given, from which we calculate the effective prestress is equal to 827 kilonewtons. Since the effective prestress in the final design is very close to the previous estimate of 826 kilonewtons, AP, P0 and E remain same. That means the effective prestress that we are calculating at the final design is very close to the effective prestress that we had calculated from our preliminary design, and hence we did not have to recalculate the other prestressing variables, which are AP, P0 and E. We have recomputed the prestressing force, and from that we found that this prestressing force is very similar to our estimate under preliminary design. Hence, the amount of prestressing steel remains same, which is 960 millimeter square. We are selecting 10 7-wire dia strands with AP is equal to 10 times 99.3, which is equal to 993 millimeter square. and we are placing these two tendons in the two ducts. The outer diameter of each duct is 54 millimeters. Thus, based on the required amount of the prestressing steel, we are calculating how many tendons we need to apply the prestress. The tendons will be placed in two ducts where the outer diameter of each duct is 54 millimeters. The specification of ducts is available from the supplier, and based on their tables and how many strands we can place in each duct, based on this information we can select how many ducts we need to place the total number of strands. We are calculating the compressive stress in concrete. At transfer, the A should be greater than P0 times H divided by F Cc allowable times Ct, and once we substitute the value of these variables, we find that A should be greater than 158976 millimeter square. At surface, the area should be greater than Pe times H divided by FCC allowable times Cb, and once we substitute the variables, we find that A should be greater than 15364 millimeter square. Thus, we have two conditions for the area of the section, and we select the higher value out of these two. The governing value of A is 158976 millimeter square, and since our section had an area of 150,000 millimeter square, the section needs to be revised because the area is smaller than what is required based on the allowable compressive stress. That means at this stage we find that our trial section is not satisfactory, and hence we need to change the dimensions of the section to satisfy the requirement of the area. The width of the flange is increased to 435 millimeters. The area of the revised section is 159,000 millimeter square, which is greater than the required value. Now at this stage we can have another set of calculations with the new geometric properties, but we are skipping this step in this presentation because those values come very close to what we have calculated, and the amount of steel that we have provided will found to be satisfactory. Hence, our design cross section looks like this, that the width of the top flange is now 435, which we have increased from the earlier selected of 395 millimeters. The total depth, we have satisfied the requirement of 920 millimeters. The breadth of the web and the depth of both of the flanges are equal to 100 millimeters. We have located CGS as down as possible, satisfying the requirement of no tension in the section, and we are locating the CGS at a depth of 290 from CGC. We have found that the total amount of steel that is required is satisfied by 9 numbers of 7-wire strands, and they are placed in 2 ducts. One can have 5, another can have 4. The tendons can be placed close to each other about the location of CGS, satisfying the minimum distance between the ducts, and like this we can provide the prestressing steel inside the concrete section. The effective prestress at transfer should be equal to 994 kilonewtons. Thus, we have designed a type 1 section based on the design requirements of the moment, the depth of the section, and the allowable stresses for concrete under compression. In today's lecture, we studied the design of sections for Flexure. Specifically, we studied the final design of type 1 members. First, we had reviewed the preliminary design, and we found that after preliminary design, we have a trial section, the self weight of the member, from which we calculate the total moment. We also have an estimate of the lever arm, from which we calculate the effective prestress and the area of the prestressing steel. After the preliminary design, we move on to the final design. Now, the final design is based on the type of section, and we have seen that the code allows us to design 3 types of prestressed concrete members. In type 1 member, no tension is allowed at transfer or at service. In type 2 members, tension is allowed, but it should be limited to a certain value such that there is no cracking in the section. And for type 3, there can be cracking in the member, but the tension will be limited to a value such that the crack width is limited and we do not have serviceability problems. Now, we have also found that the type 1 members and the type 2 and type 3 members fall in 2 different groups. In type 1, we are having no tension, whereas in type 2 and type 3, we are having tension. We are learning these 2 types of members separately. Today, we learned the final design of type 1 members, that in the final design, the first variable we calculate is the eccentricity. We calculate the eccentricity from the condition that the compressive force shifts up from the CGS to the current zone, and to have an economical section, we are maximizing E such that C is at a location of the bottom current point at transfer. From this condition, we have found out an expression of E, and once we know E, we are calculating the effective prestress, which is equal to the total moment mt divided by the shift in the C from the CGS to the uppermost point that is possible. Now, for a type 1 member, the uppermost point of C is at the top current point, and hence we are able to maximize the lever arm such that the prestressing force is less. Now, once we calculate the effective prestressing force, we can calculate the area of prestressing steel required based on the effective prestress, and once we have calculated the amount of prestressing steel, we can recompute the eccentricity by a new value of the prestressing force at transfer, and if the new value of E is similar to the previous value of E, then we are satisfied with the values of the prestressing variables that we have computed. If the new value of E is different from the previous value, then we may do another cycle of computations for the prestressing variables. Next, once we have known these prestressing variables, we have to satisfy the compressive stresses in the section. And to satisfy the compressive stresses, we have seen 2 conditions for the area. One, to satisfy the compressive stress at the bottom at transfer, and another to satisfy the compressive stress at the top at service, and the area of the section has to be greater than 2 values. If our trial section satisfies these conditions, then it is okay, but if the trial section is not adequate, then we have to revise the section such that we meet the conditions of allowable compressive stress, and we may have to do another cycle of the computations of the prestressing variables. We learned a special case of type 1 members, that trying to maximize E based on the lowest possible location of C at transfer may lead to a value which violates the cover requirements, or it may even lie outside the section. Now, in such a situation, we have to calculate E based on the cover requirements, and in that situation C will not lie at the bottom current point, but C will lie somewhere within the current zone, and our stress block is not triangular, but it is now a trapezoidal. From there we found out a new value of the stress at the bottom, and since that stress has to be less than the allowable value, from there we found a condition of the area of the section. With this knowledge of the final design of type 1 members, we studied one design problem. In the problem, the total moment and the depth of the sections were given. The allowable stresses were given based on the grade of concrete. The properties of the prestressing steel were also known from the type of steel that we get from the supplier, and the effective prestress and the prestress at transfer were given. We first did the calculations for preliminary design, and we found that we need an area which is equal to 150,000 millimeter square. We selected an I section with a certain flange width, and we had satisfied the height requirement of 920 millimeters. Now, once we have got the trial section and an estimates of the prestressing force and the area of the prestressing steel, we calculated the geometric properties of the section. Once we know the geometric properties, we moved on to the final design of the section. What we found is that this section was not adequate to satisfy the allowable compressive stress in concrete. The area required was larger than 150,000 millimeter square. Hence, we had to update the section. We increased the flange width and maintaining the height to be 920 millimeters, and we can recompute the geometric properties and the prestressing variables once again to come to a final solution, but it is found that those values are very close to the values that we had calculated earlier. Hence, the prestressing variables that we have calculated were satisfactory, from which we calculated the number of strands we need and the total prestressing force that we need for the section. With this, we come to an end of the design of type 1 members. In our next class, we shall move on to the design of type 2 members, and as I had said earlier, that the type 3 member is same as type 2 members, except that the allowable stress is different. Today we are ending this lecture at this point. Thank you.